want to try to with that, I would love to learn that.
Something like here.
Yeah, I don't know.
Thank you very much for
I mean, there's yet another very, it's not very.
I'm actually considering I have to make some changes, but I realized
To predict,
it's
like that website, someone's like,
the way
one example was
I wanted to make some revisions and send you an update on it.
so it's no more of this stat stuff, like, give me one record and here's all the data stuff, but it's, no, there's a chain of events, it's complicated. And
It's been very useful. Interesting to see what people say. Don't worry about it. I can send you an update.
I've heard of it, but I don't know exactly what it does.
They were British engineers, gives you the whole flow.
By time, by.
Right, you can see all this, and from here, many people.
Good, how are you?
But they don't see the map.
Right, yeah.
And some people say,
Maybe
That's the it's a missing.
sleeps pretty well, so
Well, that's wonderful.
she's only waking up like once a night.
Especially
Yeah, so
computer science and tech are very.
Yeah, it's good.
yeah.
So we really can't complain.
How does it work?
But it's just
But it doesn't.
when they're both around, it's all one.
Association
How
rules.
did they invite the first one?
It's very similar.
So
They're like,
DAX
we have some
style,
apps,
like
like
DAX graph
tracking
style.
like when, basically
You know, the guy who invented
But
it,
then you can
reading.
and we look back at like where Hugo was when he was the same age, it's almost exactly the same schedule.
Yeah, it's great.
On that.
Yes. That's where I learned about all of this.
Hello everyone, I'm see how the applied statistics workshop. We meet every week in this room at this time at noon. If you're not on the listserv, you can email me. My address is on the board, and we can get you on the listserv. So keep that in mind. Yeah. So today we welcome Matthias Sinning, who's joining us from Australian National University, where he's an assistant professor at the School of Public Policy there. And today he's going to talk with us about analyzing the distribution of treatment effects. So please join me in welcoming Matthias.
Thank you all for coming and taking the time to listen to my talk. I hope it'll be interesting for you. This is very much a work in progress, and comments are very welcome. So if you have any comments or suggestions to improve my paper, I'd be very happy about that. I should also say that there's a draft paper. For those of you who've received a copy of the draft paper, there are still a number of mistakes in there, and I'm happy to send you an update in a few weeks. Please don't look too closely at the draft paper at this stage. So what this is about is what I'm trying to do here is to estimate quantiles of the distribution of treatment effects. And initially, I have to clarify that this is different from estimating what people typically call quantile treatment effects. So I can write here, just if I say I have a distributional statistic, it could be some quantile or something else of a distribution of treatment outcomes, assuming I have a continuous outcome variable, and I subtract quantiles of the distribution of control outcomes. This is typically, in the literature, is typically called quantile treatment effects, so you can't see it. And the focus of my paper, or what I'm trying to do in the paper, is to look at the quantiles of the distribution of treatment effects, which is quite a different thing. Just to give you an example for the interpretation, if I look at the so-called quantile treatment effects, let's say I look at the median and I'm interested in the effect of a welfare policy on people's income. If that parameter is positive, then it would tell me that at the median, for example, that the income of the median person has increased as a result of my welfare policy. Whereas this parameter here, if the median effect is positive, it would tell me that at least 50% of the people in the treatment group have improved, have benefited from the treatment in the sense that their income has increased. And it's quite a different interpretation, but it's the reason why I got interested in estimating these parameters here, because they tell me something about the proportion of people in the treatment group and also the proportion of people in the population that are better off as a result of the treatment. And I can also look at the proportion of people that are worse off as a result of the treatment, or the proportion of people that are not affected significantly, for example. So that's essentially what I'm trying to do. It doesn't mean that the quantile treatment effects are not interesting. I think that it's quite interesting in some contexts to look at median treatment effects. For example, if I look at the effect of a tax policy on the housing market, and I want to know what is the effect on the median house price, then these are the parameters I'm interested in. But very often researchers are interested in knowing what is the proportion of observation units, the proportion of people that are better off or worse off as a result of a trial. So going away from the average and saying something about the distribution will be the goal. Also, please feel free to interrupt if you have any questions in between. So just to motivate what I just said, here's a quote from Angus Deaton, who is one of the reasons why he criticizes randomized controlled trials is that he says that RCTs are only informative about the mean of the treatment effects, but we are not able to identify other features of the distribution. And that is correct, because we have to make identifying assumptions, and we will have to have a discussion about what are kind of the most appropriate identifying assumptions that we make here. But my goal actually here is to show that RCTs are, in fact, can be informative about the distribution of treatment effects under assumptions that researchers routinely make to identify average treatment effects. So what I want to try here is to use a few assumptions that are not extremely weak. I'm not saying they're the best assumptions one could make, but these are assumptions that researchers use quite often to identify average treatment effects. And my point that I want to make here is that if we use those assumptions to identify average treatment effects, then we should also consider using them to look at the whole distribution, because we're not actually, it doesn't cost us anything more because we're already making those assumptions anyway. Okay. So the aim of the paper is to estimate quantiles of the distribution of treatment effects, and my main identifying assumption is that treatment assignment is based on observed characteristics. And in the literature, it is also known as the conditional independence assumption, or unconfoundedness assumption, or selection on observables assumptions that people have used. And I will use that assumption in combination with Gary King's approach of using coarse and exact matching, because the properties of the matching approach are very useful for my approach here. And I'm particularly interested in also looking at matching and stratification as two separate issues, and the coarse and exact matching approach is ideal for that, because it allows me to look at matching and stratification and keep these two things separate without making any implicit assumptions or combining things as I would in matching approaches that are based on simple random sampling and on exact matching. But I'm going to say more about that in a few minutes. I will also assume, and that's something I really like your opinion on that, I will also assume that the data generating process is not just based on stratification, but also that I have independence within each stratum, that the data are being drawn independently within each stratum. And I will show you in a few minutes why I'd like your kind of views on these assumptions, because I'm not sure if I have to make additional assumptions or if the assumptions that I make at the moment are sufficient. So it'd be interesting to know what you think about that. Now, before I talk about further details, I want to show you a figure. This is essentially where I want to go. In case you have to leave early, this is ultimately what I want to do. This is an example data set. This is the fairly famous Roland data set, actually from the 80s. I think the data is even from the 70s. And Roland, in his paper 1986, looks at the effect of a labor training program on post-intervention income. And income is measured on a continuous scale. And many papers have actually used this data set, both the experimental and the non-experimental version of this data set, to estimate and re-estimate these average treatment effects and to test all kinds of issues related to matching. Now, the matching here is fairly straightforward because I'm using an experimental control group, but the Roland data set also has a non-experimental control group. I will show you the results later. Now, the point, or what I find interesting here, is that I can estimate, I can use matching to estimate the average treatment effect. And in my example, after using coarse and exact matching, I get an average treatment effect of about $1,700. So attending the training increases income, post-intervention income by $1,700 on average. Now, many people have used the data set, but I think no one's actually figured out that there's a fairly large fraction of people who experience a negative treatment effect. So what you see here, the solid line here, this is actually my treatment effect across the distribution. I'm going for the quantiles from 0 to 1. These are the quantiles. And I've plotted here how the treatment effect evolves across the distribution. Now, by definition, one thing that is should be clear is that this has to be increasing monotonically. It cannot be falling because the quantiles of that function have to have the property that this function has to be monotonically increasing. So if you look at quantile treatment effects, the conventional literature, you would look at a graph where you have effects that go up and down, right? But that's not the case here. I can get a function that is monotonically increasing. Now, this point I find quite interesting. I can see here that 51% of the people in the treatment group actually experience a negative treatment effect, and about 40% of them experience a significantly negative effect. And that is always relative to comparable people in the control group. So what this graph shows you is the difference between the treatment and control group, but because I do matching, the comparison is always relative to comparable people in the control group. Okay, that would be my interpretation. So I'm essentially, this gives me like a descriptive picture of like the entire distribution, not just the average, but also other points of the distribution. Then the question, of course, is why is it interesting? Well, in this example here, this would tell me probably that quite many people shouldn't have participated in the training. Maybe they should have just continued looking for a job, or maybe they should have just done something else other than this training here. But I can also see that quite a few people are actually significantly above the average treatment effect. So for some people, it's been quite positive to do the training, but for others, it's not been positive. It's also, there are a few people, maybe this area here, around 20% of the people that don't experience any significant effect. Now, of course, you can ask the question, and I guess the first question you would have here is, who are these people, right? Who's at the top of the distribution? Who's at the bottom of the distribution? Unfortunately, my approach is anonymous. It doesn't tell you where people are, at least so far. I mean, this is an extension. It'll probably be in another paper because it would become a bit too much to discuss it in one paper. But of course, an interesting question is, who are the people at the top of the distribution? Who are the people at the bottom? What are the characteristics of these people and so on? But I haven't looked into that. There are new approaches that look at not just treatment effects heterogeneity, but also use machine learning to try and make predictions and so on. So I guess there are a number of ways of trying to address this issue, but I'm not doing that in the paper. I'm only trying to get this distribution here, and it's anonymous. Yes.
So I guess I'm not sure I understand why it would be anonymous. I mean, you know what these data points are, right? You just haven't done you haven't done anything where you've aggregated it, so we can say things. Okay.
Absolutely. No, you're right. I could look at the sample of the people below and above that 0 threshold and just compare the characteristics and just see if are there any significant characteristics. If I just do a mean comparison, I think I've done that once, and you don't see big differences in the observed characteristics because some old people are down here, but maybe some old people are also up here. It's heterogeneous. It's a lot of heterogeneity, so it's not clear cut. But I agree, it's possible to do, and it will be at some point. I just haven't done it yet.
Is it labor market income that you're measuring, or I mean, if the people had 0 labor market income, but $15,000 or $5,000 in 1972 of social benefits, then they ended up getting a job. But I'm just wondering, is it labor market income or total income?
This is wages.
So would have people who are going up from 0 to 20,000.
Yes. For that matter, it must be annual income, actually. I would have to look up the exact definition. Sorry, I can't remember it, but I think it's annual income. Okay, so before I start talking about how I derive this graph, I should briefly mention what others have done in the literature. Assumptions that were used in the literature, like most famously, the quantile treatment effects literature makes an assumption that is called rank preservation. That means we assume that observation units maintain their relative position in the distribution, regardless of whether they are being assigned to the treatment group or the control group. And in practice, that means essentially if I have 2 distributions, I have a treatment distribution and a control distribution, I can essentially just order the data. If I have a spreadsheet with the data, I can just go from, like, in ascending order. I can look at these 2 columns in ascending order, and I subtract them from each other. And that has the property that I can split up this expression here. So I can obtain these quantile treatment effects because of that rank preservation assumption. But it's a very strong assumption because it means that that I have to rank observations, and that people would maintain that every observation unit, put it that way, every observation unit, if I would move it from one group to the other group, maintains their relative position, and that has to hold for every observation unit in the data set. So it's a fairly strong assumption, I believe. But it solves the problem, obviously, because I only need to look at the separate distribution. I have the treatment distribution and the control distribution, and I just take the difference in medians, and I've solved the problem by doing that. Okay, so yeah, that's kind of what people have done for a long time. And of course, in some contexts that can be quite useful, but not always. And it gives you an interpretation that's different from the interpretation I'm after. Okay, the second literature is more related to my literature. In this literature, these quantile treatment effects are defined as quantiles of the distribution of treatment effects, and this is work done by James Heckman and co-authors mainly. They have looked at a number of ways of addressing this issue, and they've looked at many different assumptions about the dependence between either the potential outcomes or the unobservables. And they've also come up with solutions, but I haven't seen many applications of these methods, probably because it's quite difficult to apply some of them, but also some of the assumptions are quite tricky, like in practical terms at least. Now, what Heckman and co-authors have consistently done was to ask the question, how do we solve this problem if we have messy data, if we have a selection problem, or if there is strong dependence between potential outcomes because participants can make rational decisions about either being in the treatment group or the control group, and so on. But what I'm doing in this paper is to say, how do I address the problem if I have high quality data? What happens if I have good data, like experimental data as a starting point? And are there ways to make assumptions that we usually make anyway? And how far can we get with that? Now, one implicit assumption you will see in a few minutes is that I make here is that I assume independence between the potential outcomes. And that's got something to do with what I assume about how I select the data. Be interesting to see what you think once I show you the assumptions. Before I show you the assumptions, just some notation. This is the potential outcomes framework by Rubin, 1974, that I'm using here. It's pretty standard. I have uppercase letter N is the number of observation units. I have potential outcomes for the treatment group. The yi1s are the treatment outcomes. The yi0s are the potential outcomes in the control state. I define a binary treatment indicator, and then this is my standard way of writing expressing the observed outcome. And I also assume that I have a vector of covariates that I will use for the matching later on. Right? So given this framework, it's fairly straightforward in an RCT, in an experimental setting, to identify the population average treatment, to identify the population average treatment effect and the population average treatment effect on the treated. And the reason is, on average, when I look at expected values, the expected value is a linear operator. And because of that, I can just separate these two terms here, and I can say I look at the average effect for the treatment group, and I subtract the average effect for the control group, and that gives me the average treatment effect. Right? Whereas for the quantiles, I cannot do that exactly the same way as I told you. If I try and split up the median in the same way, then I get a different interpretation. I get a different result. I have to assume rank preservation in order to split these two expressions here, if I look at other points of the distribution. So that's something I have to address. Now, just to explain, these are my parameters of interest. So I define some very general distributional statistic. I call it nu of f. It's just could be just some quantile. It could also be something else. It could be like a Gini coefficient or an Atkinson index or some other measure. But I will focus on quantiles. It's just a very general notation that people have used in the literature that I'm using here. And I'm particularly interested in what Heckman and others have called the impact distribution. I'm interested in the distribution of the treatment effects. Okay, that's ideally what I like to identify. Then I can define the population new treatment effect. That's like my quantile treatment effect, kind of modified quantile treatment effect, and this would be the population treatment effect on the treated. Okay, so these are my assumptions, and I have to say I copied some of those from Gary's paper, actually, and I modified them a little bit. Now, the first assumption deals with stratification. Now, because I want to say I want to use a matching approach, I could have made an assumption that I have simple random sampling, and I could have done exact matching, but exact matching has the problem that if I match on continuous covariates, then exact matching is typically not a possibility, and then I end up with making ex post assumptions about stratification. I'm sure you all know probably more than I about these coarse and exact matching approaches and so on. So I don't want to go too much into detail, but the assumption that I'm making here is that I have I have stratified sampling, and that includes that within each stratum that I create here, my data are drawn independently from the distribution. Now I've modified this assumption a bit from Gary's original assumption, and the reason is I don't call this stratified random sampling, because stratified random sampling would mean that I create strata and then I use a simple random sampling approach within each stratum. Now, a simple random sampling approach, if I do simple random sampling without replacement, then technically I don't get independence, because it could be that because of the simple random sampling without replacement process, I'm creating some kind of dependency between my observations, because if an observation unit has been drawn the first time, it cannot be drawn again the second time. So ideally, I would look at simple random sampling with replacement. Then I have independence. But because there's a small difference between simple random sampling with replacement and without replacement, I kind of modify this whole idea, and I say I want independence. I want to make sure that I have independence, and that's why I say here I have independently drawn observation units from the data. Now, the difference, as you can imagine, is typically very small, and especially if I have a very large population and my sample is very small, it's irrelevant. So I could say if my population is infinitely large, then I can actually call this simple, or so in this case, actually stratified random sampling. But I'm a bit careful because I specifically want to make this assumption that I have independence within each stratum. So that's the assumption about what happens within the strata. And then I can make two additional assumptions that I also copied from Gary's paper. One is the set-wide weak unconfoundedness assumption, and the second one is the set-wide common support assumption. Now these are strata versions of the common unconfoundedness assumption and the common support assumption that people usually use. And in fact, if you have exact matching, then these would be equivalent to having like what Rosenfeld and Rubin call the strong ignorability assumption that they make. Now, the assumption that I'm not making, I'm actually looking at you because we had this discussion on Monday. Xiang actually said to me, well, the assumption that I should be making is actually the assumption that the potential incomes, the potential outcomes given X, or given X element A, are independent from each other, because that's ultimately what I use for identification here. I'm assuming that my potential outcomes do not depend on each other. And my question is then, do these assumptions cover that? And I believe they do, but it'd be interesting to know if I have to make that assumption explicitly. So the assumption would be, I can just write it here, that my potential outcome is independent, so the two potential outcomes are independent from each other given X element A. So I would assume that explicitly. But I believe because I assume that I have independence within the strata, and because I'm assuming that within each strata, assignment to the treatment group is as good as random, that's essentially what this assumption tells me here, the weak unconfoundedness assumption.
Since you have an experiment, I don't understand why you have to make assumption 2. Since you,
Yeah.
by definition, are randomly assigning the treatment, so why do I have to do assumption 2?
Good point. And it's again related to this assumption here. I'd like to make this assumption. I'd like to say my potential outcomes are independent from each other within each stratum. I don't want to make the assumption that they are independent from each other in general, because that's a very strong assumption, whereas saying within each stratum I can compare the matches that I get.
So
it's a much weaker assumption.
So you want some correlation.
But I have a discussion of that in the paper, and it's actually quite an unfortunate discussion. I think it's actually, we're better off without dropping it. I think it's a good idea to keep this assumption. First of all, in practice, even when we have a randomized controlled trial, we still want to balance out characteristics, because there are always some differences in observed characteristics. And often RCTs are even based on stratification even before the implementation of a trial. I've done a few trials where I had baseline data and I was able to stratify and randomize at the same time. So it makes a lot of sense to make this assumption, to balance out these characteristics in practice. But I agree with you, theoretically, you're right. Theoretically, I don't need this assumption if I have the ideal experiment, and I've tried to discuss that in the paper, but I don't like the discussion. But
it doesn't have to do anything with the fact that you do want to have some heterogeneity arising from the X's and the Y's. Is it sort of implicit maybe that, or am I just reading it too much?
No, I think you're right. You can assume that. It's fine to assume it. People do that actually. People make the assumption that throughout the whole data set, the data are drawn independently from the distribution of the population, full stop, without stratifying. But I believe in my context, this would be very strong to assume that I can say, I allow people from the treatment group to jump wherever they want in the other group if I move them. That's why people make this rank preservation assumption where they say you have to stay in your relative position. I essentially say you have to stay within your stratum. Don't move too far away.
A stratum would be like values in X's, right? Sort of.
Yeah.
So are you saying that these assumptions imply this, or?
I hope that. You don't think so? Okay. In that case, I would have to make this assumption as an additional assumption. But
right. I guess the other question is maybe more fundamental. Is how do you pick X, like IA, I guess? How do you know, like, to guarantee this assumption? How do I choose X?
Well, if you do matching, like many people have done matching and
yeah, but it's a little bit different because this is like the two potential outcomes which you never observe at the same time.
Right.
So how do we know the set of X that guarantees, or is there diagnostics that? But it seems that choice of variable is critical.
not sure if I can follow.
I mean,
of course, the choice of X.
like if you include too many X's, this could be wrong too. Like suppose independence holds only conditional on say gender and race, but if you end up including say age, then there's not, now all of a sudden the independence may not hold. So
why is that? Because this is not causal. This is not about. There's the same logic about causality doesn't apply here, because these are you're independent between two potential outcomes. It's like, what's my income? What's the relationship of my income under treatment versus my under control? Those are generally going to be correlated, but like there's maybe a set of things under which they're not correlated.
I mean, that's the whole difficulty of this heterogeneity, right? Heterogeneous effects is that in the kind of like the issue of confounding you could make an argument that, well, what I'm trying to do is like making the treatment group and control group as similar as possible. And even though mathematical conditioning on too much could be bad for the unconfoundedness assumption, you could still at least intuitively argue that, well, if I make two groups similar, that's a good thing. Here it's like that logic doesn't even apply, right? The independence could break down, like who knows, like what, and you can't never observe two at the same time, so you have very little, power to figure out what that conditioning set is. So I don't really know.
It's interesting. I mean, we're meeting afterwards anyway, right?
Yeah,
So we
okay.
can have a chat.
Okay.
Is it?
You better figure
I wouldn't.
I mean, one way you could think about, I think you could think about this assumption is, if you had magically potential outcome under control, you just want to condition on that, right? And conditional on the potential outcome under control, it's like a baseline covariate. If I knew magically, or it's like over time I could measure you before, and that was a good proxy, then this would kind of hold by, and I condition on that in the X or an A or whatever, this would kind of hold by construction, because they have to, because you'd be conditioning on it, so that it would like, you would not need this, like, it's just yi is a random draw, essentially, I think. So it seems, this is my intuition about that, and it seems like there, you could try to come up with an intuition about what kinds of things should go into X. It's like the things that would try best predict the potential outcome or control or under treatment or something like that. And I just don't, it's just like one, it's not guaranteed. If you're just off of y of 0, it may not work, but maybe that's an intuition.
Suppose we invert things. So both potential outcomes are figments of our imagination, right? We just made them up, right? And we know both can't exist, so we have no evidence that they're just made up. So Mathias would like to say that assumption holds, but maybe an alternative way of saying it is, well, in some world it holds, right? What's that world, right? So maybe we could just think about that. Like, in other words, his estimates are, it's not like his estimates, or one way of saying it is his estimates are wrong if that doesn't hold. Another way of saying it is his estimates are right, conditional upon a particular interpretation of that. So could we figure out what the interpretation of that is? Well, we sort of know what it is, it's that. But I wonder if there's a way of expressing it clearly so that you just basically get to interpret the estimates you get.
Seems just a conditional effects, like group effects within that set.
Yeah, group it.
So it's not an effect for each person, but it's just the effect of.
But that's what he's trying to do in a sense, right?
But he's looking at the distribution of individual effects, which is not identifiable.
Right.
You could order this straight up.
But maybe you can tell us.
Yeah, if we don't, seeing that
I
method.
don't want to. If I have a chance at the end, maybe I can tell you a bit more about my thoughts. Why I think
how
that the potential, what I think the link is between the potential outcomes and the observed outcomes.
Okay.
But let's, let me go through and first discuss my approach. But then I have a few, I have some bonus material if I have time. Okay, so I'm using the coarse and exact matching approach. I don't have to say much about that. Coarse and exact matching uses each covariate to assign observation units with similar values to the same group. Essentially, I'm creating strata, and then I do exact matching within those strata. And I may have different numbers of observation units in each stratum. I may have different numbers of treatment and control units in each stratum. But essentially, the matching that I do, and you could keep these two processes actually separate. You can think about matching and stratification as two separate issues here. But the matching is done in a way that I match within each stratum. I match all the treatment units to all the control units. Right? And that has a certain property, and that might have something to do with that actually. But let me come back to that later. Now, this is the type of matching that I make because I say I have independent draws within each stratum, so it makes perfect sense to match all possible combinations to each other. And in fact, that's something we actually do implicitly when we estimate average treatment effects as well. And, I'll show you first my results for the average, and then I move on to the distributions. One thing I should briefly mention, because the coarse and exact matching approach involves removing some strata from the sample, because sometimes we just don't get a match for certain strata. Some of the observation units are being removed from the sample, and that's why we're estimating feasible versions of our estimated parameters of interest, but I don't see that there's any issue with that. If you do the coarsening properly, then you don't lose many observations. Typically, it's a question of how you set up, how you use this approach. Okay, so now I wanted to write down the matching, but essentially what I just said is what I've written here. I'm matching every observation in the treatment group to every observation in the control group within each stratum. Like if they belong to the same stratum, if they have the same coarsened characteristics, then I match them together. And my notation here is that I say I have, like, let's say for the treatment group, it would be yi1, and then for the control group, it would be all the matches, all the possible control matches that I have in the same stratum. I match those together. For simplicity of my notation, I can define a certain set. This is the set of matches here, but I can replace that actually and say this is a broader set. I could also assign, I could redefine this as being yjd instead of yid, and that makes my notation a bit simpler, because then I can just write these potential outcomes as yjd for a slightly different set of observations, and it makes it easier when I subtract them from each other. You'll see it probably on the next slide. Yeah, here you see I'm using this notation then to subtract treatment and control units from each other. So what you see here is my way of estimating or identifying the population average treatment effect. So this is all written in terms of population strata and population number of observations and so on. I can write this population average treatment effect for a single stratum A. So this is not the full population average treatment effect, but this is for each stratum. I can derive this formula here and say within each stratum I do the matching, I subtract all possible combinations from each other. I have some weight. My weights are actually slightly different from the standard SEM approach. My weights are based on the number of matches, but it kind of is similar because it gives you an indication for how large these strata actually are. And then I just take the average within each stratum, and that gives me the average treatment effect. So it's essentially a way of a different way of writing the average treatment effect. And it gives you exactly the same number that you would get from regression analysis. You can compare these average treatment effects to my average treatment effects. You get the same result, which is reassuring, of course. But it also shows, this formula shows you that in the matching framework here, you can actually obtain the average treatment effect without having the property that the expected value is a linear operator. You don't have to separate y1 from y0. You can get that differential here, and you take the average of the differential, which gives you the average treatment effect. So separating these two expressions here is not actually necessary. I think that's quite an interesting finding in itself. And I want to exploit that fact, of course, for my distribution. Because if I separate these two, there's no way I can get them back. And if I want to look at distribution, if I want to look at quantiles, then this is the way of writing the average treatment effect. Then last step, of course, I've done this within each stratum, But then, of course, we know we can also get from each stratum to the overall average treatment effect using the law of iterated expectations. We just take the weighted average over all the strata, and that gives us the average treatment effect. Okay. Now, the next step is actually I'm applying something that makes my life a lot easier. I'm moving from the nonlinear quantile world to a linear world in order to exploit this equation here. What I want to do now is to rewrite my parameters of interest by using what is called a recentered influence function. This is something I don't want to go too much into detail here. It's been developed by Firpo, Fortin, and Lemieux in a recent paper where they use this approach or use the idea of the recentered influence function to estimate what they call unconditional quantile regressions. And out of that paper, I've taken this idea of the recentered influence function, and it essentially, without being too technical, this recentered influence function is defined as an influence function where you add back the original statistic of a distribution, and it has a number of useful properties. For me, the one property that I'm exploiting here, the one useful property is that I can take the expected value of that transformed variable here, and I get the quantile. That's a pretty cool property, and I really want to exploit it for what I do, because it makes my life a lot easier. So essentially I say W is a random variable. I transform this variable into the recentered influence function of W for a given quantile. And if I take the average of that new random variable, it gives me the quantile. And now I can combine these two ideas and say, well, I can rewrite my random variable as being the difference between outcomes. And this gives me a different notation for the average treatment effect. Okay. So I don't want to go too much into detail. If you're interested, these two papers that are, I think, really useful for this discussion. But that makes my life a lot easier, because now I'm still in the linear world, but I'm able to obtain quantiles of the distribution. And I've written down exactly how the steps that I'm following here, but essentially what I showed you here earlier for the average, this is essentially what I extend to recentered influence functions. So I say, if this is the way of calculating the average without separating y1 and y0, then I can take the recentered influence function of this expression here, and that will give me the median, or it'll give me some other point of the distribution. That's essentially the idea of that recentered influence function. And what I'm using here then is again, I'm using the law of iterated expectations. Because I'm still in the linear world, I can say, I can find the quantile within a stratum, but I can also get the weighted average over all the strata, and that gives me an overall formula for the quantile of the distribution of treatment effects. That's so far. That's actually how I identify the effect. Now the rest is about estimation. I have a few slides. I mean, the paper has a much longer discussion about estimation issues and so on. But essentially, what you can see here is that what I'm doing here is actually just calculating an average. The recentered influence function is just a random variable. It's just a transformation of a random variable, if you will. And I'm just taking the average of that transformed random variable, and that gives me the average treatment effect, the estimated average treatment effect, and also the estimated average treatment effect on the treatment.
How is this RIF defined? What transformation is it?
Sorry, I don't have it here. I might have it in the paper, but it's...
Sounds very interesting.
No, sorry, I didn't have a longer discussion here. I can't remember the equation. It's based on a kernel density function, and then you divide by a marginal density. I would have to look it up. I can't remember how it looks like exactly.
By difference in the yj1, yj0 within the strata for all the matched pairs, you're essentially using this assumption to interpret that quantity as an empirical distribution of the treatment effect. Otherwise, that quantity is not interpretable.
This one here.
Yeah, but by taking the difference and then use the distribution of that difference, you're making this assumption.
That this is the distribution.
Yeah, you're interpreting this as a distribution of the treatment effect.
Right. That's
that,
right.
That interpretation is based on the independence assumption.
Good point. Okay, if that's your problem, I have some bonus material for you. But let me quickly go through the rest before I talk about that. But yes, that's right. This is what I assume. I'm happy with that. Because I can link it, I think I can link it back to the potential
How do you
outcomes.
How do you choose A?
How do you choose A?
Like if you pick different A's, you'll get different results, right?
Yeah, of course. Yeah, but again, I mean,
Right.
that's part of the matching approach that I'm using. That's with any matching approach, that's the case. But I think you have a slightly more complicated thought in mind. And maybe we should discuss it later because
It's very simple.
well, how do you choose? Well, I would match based on observed characteristics that make sense, whatever can potentially influence whether you're in one group or the other. Or if there are differences in observed characteristics between groups, you would make comparisons between treatment and control groups to see are there any significant differences, and these are the important dimensions that you would definitely take into account when you do matching. But this is just an answer to how I would do the matching, what characteristics I would choose there.
I think the problem is that those balance, so balance between treatment and control doesn't necessarily, so I think what Kosi's getting at is that balance between treatment and control doesn't have any bearing on this assumption.
That's right. Exactly.
Right, so I think that's, I mean, it's separating it out, like, do you need, like, so one problem could possibly be that it's not feasible to construct, so if you're not in a randomized experiment, if you're in an observational study, I wonder, one, is it feasible to create a conditioning set that both satisfies unconfoundedness and satisfies this assumption? It may not be possible.
Yeah.
So that's one thing. But second law, if it's targeting the two different things might lead to very different intuitions about what you should condition on. It seems like, and it just in the context of the study, it just seems very hard to. I don't know what I need to condition on in order for my income under both programs to be completely uncorrelated.
Right.
It just seemed like those seem like very dependent. A lot of things about me.
Right.
They're gonna induce those correlations, and I don't know what it would be that would break those.
Obviously, it gets harder the more you have to take that into account in the matching context. But I'm not sure. Yeah, it's a good question. Is it the same? Is moving from an experiment to an observational study similar to for the matching, for the standard matching compared to what I'm doing? Like,
I don't think you have. I don't think you have. I mean, I don't know what diagnostic you would use. I guess. Like, so I think that's like I don't know how to evaluate. So technically, it's not like you can't evaluate the proper balance of matching either because you don't have potential outcomes. But we do it through covariates, and I just don't know if it's same. The same thing can be done here.
It's the same thing. Right, I can't answer that right now, but that's an interesting question. All right, let me just show you the kind of part of the estimation, and then I can show you some results that I've produced based on that. So I can rewrite this. Obviously, one of the problems that I've kind of introduced myself here is I'm not just looking at an average. I cannot just calculate the average and look at the the normal standard errors of the average, but I've introduced dependency between observation units here because of the matching, because I'm matching within strata. And as a result, what I'm doing then to address that issue is to rewrite this average here and say, well, I sum up over all the strata, and then within each stratum, I'm summing up all these numbers that I have within each stratum. And that brings me to a different way of kind of calculating, or the correct way of calculating the standard errors, because the standard errors then that I use are clustered standard errors, where I say I use a large number of clusters framework where the number of strata goes to infinity and also the number of observation goes to infinity. And within that framework, I can obtain clustered standard errors for these estimates. I'm using this asymptotic theory of Bruce Hansen and J. Lee, which I think works quite well for my approach here. They have a fairly general, they look at a fairly general asymptotic theory where they allow the number of strata to diverge at a slower rate than the number of observations. And they allow these cluster sizes, within cluster sizes, to diverge to some extent. But overall, because they maintain that assumption that, or they consider the case where the number of strata goes to infinity, essentially, and the number of observation goes to infinity, these cluster sizes diverge, but they are always like irrelevant relative to the size, to the total sample size, and relative to the number of strata overall. The details are in the paper, and I'm not going to talk more about it. But essentially, what I'm getting are clustered standard errors that I can use between, and these are implemented in standard software packages. Okay, so here's some results from the Lalonde data set. This first part of that table here just shows you some descriptive statistics of the raw data. You can see here that the raw gap in the experimental data set is about $1,800. That's the effect, experimental treatment effect, the average treatment effect. If I don't control for anything, there's also a non-experimental data set that Lalonde uses. The one that I'm using here is actually the largest. Several non-experimental data sets. I'm using the CPS sample that he provides because it's fairly large, so it makes it easier for me to do the matching. You can see here that without any correction, this is quite different. The non-experimental data set is quite different from the experimental data set. And then I can do coarse and exact matching to make these differences more comparable, or to make these groups more comparable. And I get a raw gap of about $1,880 here for my experimental data set after the matching. Shouldn't be very different because the matching shouldn't make a difference, and of course it doesn't, but it does make a difference for the non-experimental data set where I get a raw gap of minus 1,300. But then I can look at the average treatment effects after the matching, and I get average treatment effects that are about $1,700, or in this case about $1,300 to $150 on average. Now, what I've written down here, the horizontal, what I call the horizontal distance, these are essentially the quantile treatment effects according to the conventional definition. And they are increasing across the distribution, but they could go up and down. And if I would calculate more of them, they probably would. But then here, what I call treatment effect in this table here, these are the treatment effects that I calculate according to my definition. And you can see that they're also monotonically increasing, and they have to be monotonically increasing by the way I defined them. Anything else I should mention here about this? Well, perhaps one thing that's interesting is that these two are the same, because on average, of course, I have to get the same treatment effects from these two definitions here. I get slightly different standard errors, and the reason is that here this horizontal distance, this is essentially like a coefficient that I get from a regression model. Where I have a slope parameter for the treatment dummy, whereas this is actually the standard error that I get. Well, it's a clustered standard error too, but it's also a standard error that I get from a regression of the differential on a constant term, essentially. I'm keeping this differential together. That's why the standard errors are slightly different. It's true for both for the quantiles and for the average effect. You remember I said initially I'm calculating the average treatment effect by keeping the y1 and y0 together instead of separating these two out. That's where my approach is slightly different. And that affects the standard. Okay, this is the graph that I've shown you earlier for the experimental control group, but I can also reproduce that graph for the non-experimental comparison group, and you can see that the effects are not completely different, slightly, the average effect is slightly lower, but overall the picture is fairly similar. I still find that about 50% of the people are below and 50% are above that zero threshold. I can show you, I've done a few more applications, because now, I mean, it gets interesting when you are able to use this approach for different RCT data and so on, and I looked around what's available. I could find a data set by Angris. This is the Project Star data set that he made the data available. And I could re-estimate his average treatment effect and then look at the distribution. This is the effect of a student fellowship program on average grades. And you can see that across the distribution is a lot of heterogeneity, essentially. Why that heterogeneity exists, I don't know, but you can see that not everyone benefits relative to the comparison group, simply because there's treatment response heterogeneity. Different students will respond differently to receiving the same treatment. I've also tried it out to use the approach for an example where I don't have a randomized control trial, but where I have to use the matching approach. This is a data set by Cataneo from Journal of Econometrics, where he estimates the effect of smoking during pregnancy on child birth weight. And you can probably imagine that assignment into the treatment group, smoking during pregnancy, was non-random. So there's clearly a difference between the treatment group and the control group here. So you have to use a matching approach to balance out some of the differences, and you can control for things like education and social background and income and so on, to make pregnant women who smoke and who don't smoke somewhat more comparable. I find that on average the treatment effect is minus 250 grams. So if mothers smoke during pregnancy, then the children will on average be 250 grams lighter. But I also find that in the worst case, for some women, the effect is up to 1 kilogram. So it's actually dramatic. I also find that for some women, they happen to have heavier children just because there's heterogeneity, and that's why I see this pattern.
Just trying to map back the quantile to the math. So what is the quantile over? Is it over the full space of A, or what are we quantiling over?
Yes, it is. It
It's
is.
like
At the end
collapsing
of the
the full
day,
space of
it's
A.
the quantile over the full space. Yeah.
Okay, so if it's okay, so it's like a 5-dimensional A. We are reducing it to 1 dimension and then taking the quantile over that. Okay.
So there's a group of people here who you treat them by having them smoke conceptually, and they have kids that are healthier.
Well, or heavier at least. And
That's a pretty good measure. I mean,
yeah. No, that's right. But does it mean that we should take up smoking during pregnancy? I don't think so.
Well, I mean, you should be careful about doing the next paper you promised, where you're going to tell us which types of people.
That's right. Yeah. No, of course.
I mean, that's because you would expect maybe to find some below and some above the line, but you'd expect the standard errors to be the confidence intervals to be much larger. So, are those do you believe the narrow uncertainty intervals you have? That's quite a term. I mean,
Yeah, they're quite.
let me ask my favorite public health person.
No, I think if you smoking is a hard one to kind of anybody would say you shouldn't, but if you could take any drug that is supposed to be therapeutic, and if people are getting hurt, it's the same. Even if a decent proportion is getting the benefit, and so on average it does look good. So it's kind of, I too worry about, you have a pretty tight confidence
You're right,
interval
yeah.
here.
As I said, these are clustered standard errors. So whatever I do to calculate the average effect, I apply to a few other points. I think I've calculated 20 points across the distribution. I didn't want to be too precise. I mean, obviously, if you estimate 100 treatment effects, then in 5 cases, the 95% confidence interval will be wrong.
No, but my point was, so that is a real effect.
This is what I find, yeah.
For the top end of your distribution space.
Yes.
There are
But from
people
from what we know substantively, is that conceivable?
it's like, so
Well, but again, this is heterogeneity. Like different people respond differently to the same treatment, and it may just happen. I can't tell you why, right? This
I mean, it
doesn't
is
tell you
possible in
anything
the
about
sense
why.
that I don't think we fully know there is the entire mechanism through which, on average, yes, it's supposed to lower the birth weight.
This is a
I mean,
third of
it's-
people,
Yes.
right? This is a third, almost a third of the population is above this, right? That's a
It's a lot.
That's a lot.
I mean, there's also some evidence with smoking, like it's protective of type 1 diabetes.
Really? For the kids?
For the kids in pregnancies if the mom smoked. So in Swedish data, we've seen that one. So it was like a hard time publishing it. But, I don't think we at some point we gave up.
You have to eat a lot of Swedish fish.
Exactly. So yeah, this is kind of, I've never seen anything on birth weight showing this kind of heterogeneity.
Right.
So,
Well, I'm happy to go back in. I mean, these are quick and dirty
Sure.
applications of the approach. These are publicly available data that you get actually, like within Stata, it's an example data set that you can use for matching.
So can you kind of, once having found this, go back to your sample and see based on the covariates, is there something kind of different? I know you matched it out in some sense.
I'm happy to have a look at it, but
So
I might try and get the original data too. I mean, this is really a Stata example data set that I'm using here.
I have just one. So if you have to do this like as a multinomial, would this be any different? Like, I break up my the y into instead of on the mean, like, the bottom 20%. Would that, and then just run an ordered or an unordered multinomial, I guess. Would that be any different from a quantile?
That's a good question. Yeah, interesting.
Like just a standard unordered multinomial, it'll give me different intercepts, it'll give me different slopes, right?
Good question. I should look into it. That's a good point. Thank you.
Not collapse the quantiles and maybe keep, like, just do the quantiles on the dimensions of A. So my previous question was about the quantile, and you said it's sort of a summary statistic of the high dimensional distribution. Could we just essentially plot the quantiles for each dimension so that we get a better sense of what's going on over the space of A?
Maybe. I haven't thought about it.
It sort of answers a little bit the question you posed.
So you wouldn't look at the quantized for each stratum?
Yeah, because
There's a lot of that's
right, it's a lot of it, but I mean, but if you might look for the relevant, so 1/3 is having a beneficial effect, you might want to look at maybe diabetes, if diabetes is in the data.
Right.
And then be a little bit more careful about when you collapse the quantiles.
Okay, that's a good idea. I mean, obviously, there are many possible
So
extensions.
these-
I haven't done any of
No,
those.
it's cool.
So the
Should I just wrap up?
sure, yeah.
It's just.
I have 2 more slides to go. This is some of my own work that I've done last year together with Christian Gillitzer from the University of Sydney. And We did a longer paper, but because I had the data, I was just straightforward to try this kind of thing. We didn't look at the heterogeneity in our paper. This comes out of a project that I've done with the Australian Tax Office, and we did an RCT where we send out letters, reminder letters to taxpayers, to remind them to pay, that they had forgotten to pay their taxes. And we looked at in our paper, we only look at the average effect of sending out letters to taxpayers. And overall, we find an effect of $468. That means if you send out a reminder letter, then the tax payment that takes place according to administrative records is 468 on average. But then also, you can look at the distribution. You also look at other issues like the timing of the letter and so on in the paper, but this is our main effect overall. And when you look at the distribution, you can see that for most businesses, they do pay more taxes if they receive a reminder letter. But again, we find that for some businesses, we find a negative effect relative to comparable businesses in the control group. Our explanation for that would be that if someone receives a reminder letter from the tax authority, then it may happen that they believe that they will receive further communication regularly, and they will just procrastinate and delay their response as a result. So this is the overall pattern. Just to show you that I get different results for different data sets. There's a much more detailed paper that we've written on this trial. Okay, let me just wrap up. What I'm proposing here in this paper is an approach to estimate quantiles of the distribution of treatment effects, and I assume that I have treatment assignment that is based on observed characteristics, which allows me to use a matching approach. I also make a number of additional assumptions, and we'll have to perhaps discuss a bit more which assumptions exactly I'm making here, because I also like to understand better. Let's talk about it. The approach can be used for experimental data, but also not for observational studies. There are potential applications in many different areas, which I think might be interesting: social sciences, behavioral sciences, and also medical sciences. Obviously, more work has to be done, and it covers both applications and methods. Thank you very much. Thank you for coming.
You were studying?
Yeah, well,
The new Vikings. What is the bottom 1%
right now about that.
of the effect
Ron
that
saying,
will have?
we just did that, and they were flooded by
How accurately can I estimate the bottom 1%?
at least, we're talking like
Have a large-
15,000.
Yeah.
I was like,
Should I misapply that?
so we just coming back.
Well, they were the first ones that actually came. Well, after 15,000 years ago, when they came, they were the next ones. Yeah, we're
I mean, it tells you how
Always the same
everything is so relative, right?
Yeah.
Talking about national identity, which is like, it's a concept that is relevant now, but it hasn't been like, will not be.
It's just something to be,
Are you
to
American by?
give the audience more help, I say. You know,
I lived over
Have
here
some
for a
German-
decade.
when you present it. Because
My
otherwise it will
my
look
father's
like
mother
there's
was
just a
German,
mistake.
but they were here for a couple of hundred years.
Yeah, but
Yeah, yeah.
well, the question is why does it
But she
happen?
still, when I got to Germany and I like observed them, and like,
I can estimate an effect
she
for
would do things like
the
they
average.
did.
Yeah,
She still
Yeah.
changed in those cultural
I
things.
can estimate an effect for the median. I always use the same distribution. I just ask, how big is this point? How big is this point? How big is this
German.
point?
Yes.
And
That's what they do.
standard errors should be correct.
Yeah.
Like, why wouldn't they?
Let's go to
I wonder.
Sure, see. Thanks, Connor, for the food. Thanks, really good.
But you're right. I mean, there's some examples.
We'll
of
be meeting
like
tomorrow,
this
right?
example.
I see, exactly, but
Oh,
the
not
first
next
one,
week.
and the first one you put up there,
Yeah, no.
the first one in particular,
Tomorrow we have.
This one.
well, no, the one, well, you showed,
Wonderful.
at the beginning of the presentation,
usual
slide number
paragraph.
1 or 2.
Oh, yes. This
You know,
one.
they were huge, it was
I
huge
love
up
the
there
name
at the far,
Kirk.
well,
It's like
actually,
Star
only on the
Trek.
right,
Serve.
on the left, it's not very big.
Kirk Street, Kirkland?
Okay, I take it
Kirkland.
back, but anyway, some of them,
Yeah, well,
It reminds me of Star Trek, right?
But you're right.
Kirk.
Yeah, the point is well.
Kirk.
I agree.
Okay.
Thanks for coming out.
About the X's, so I was wondering, so it seems to me like some of the X's here you might want to use for identification, but some are actually not for identification, it's for heterogeneity, so you might want to.
Interesting.
Is that, like, because I'm using sort of the machine learning approach, and then we have certain X's that we use specifically for identification, and there's some bunch of X's that don't have to do with any of this, but we
Right.
want to include with heterogeneity, you say?
Yeah, right. That's
And
exactly right.
is that sort of maybe like thinking with the set of X's, and maybe that will help you circumvent? Because is this like saying
Baby
the
tried some
potential
time, it's very close to
outcome
where I live.
under control, conditional X being in certain strata is independent of, is this what it's saying, this one here?
If you're in the same strata, like these are potential outcomes in the same strata.
They're independent.
They're independent from each other.
If they're in the same strata.
If they're in the same strata. This is what
So,
this is.
so it's like essentially saying, it's not even saying the same variable, it's
No,
not
it's
saying
not the
like
same
may,
X. No,
like,
no, it's the
it's
same
not like
cell.
gender, it's
That's right.
like
No, no,
being
exactly.
woman
Yeah, yeah.
or being male, right?
Exactly.
Yeah, and then those things are independent, that's what it's saying. Yeah, I was like thinking that it's a bit of an unusual way of posing it, but I get your point. But maybe, I don't know, like I'm not sure, but it seems to me that maybe it's getting you into trouble. Maybe it's better just saying like some X's are, because they are independent per definition if you are in an RCT, not maybe an observational study. I mean, they should be per definition.
Yeah.
So you might not need this, but you want to have this